Okay, hi everybody. My name is Vanessa, and then I'm going to be doing activity 5 today for chapter 16. So we're going to be going through the activity packet, and then I'm just going to explain to you how I think through these questions. So then for the first one, the first question is actually pretty straightforward, and it's just asking us which one is isolated, which one is cumulative, which one's conjugated. So isolated is if there's more than one single bond in between two double bonds. Cumulative is that there is no single bond in between two double bonds, and then conjugated is if there's only one bond in between the two double bonds. So using that knowledge, we're going to look at our first one. Our first one is this one right here, and then we can tell that there is one bond in between the two double bonds. Same right here if you look at it that way. So this one's going to be conjugated. For the second one, we can see that there's more than one bond, and over here there's way more bonds. So we can already tell from just looking at this one right here, this one's going to be isolated. Looks better. This one right here is just a one bond in between two double bonds, and this one's going to be conjugated as well. This one right here, the C here, the carbon here might trick you, but there's no bond. In order for it to be conjugated, we would need two C's in between them, but there's only one C, which means that this one is actually not conjugated, but in fact it's cumulative. This one, last one right here, there's one double bond, so this one is actually conjugated as well. Moving on to the second one, I'm going to be ranking these in order of increasing stability. So a few rules when I look at this problem, a few rules that it comes to mind is that the more double bonds there are, the more stable a compound is. If those double bonds are in a fashion of conjugation, then it's going to be more stable. And trans is always going to be more stable than cis, just because for trans, the molecules are as far away from each other as possible, whereas cis are actually being forced to be, closer than they would like to be from each other. So using those 3 points of knowledge, we're going to be looking at this problem. So automatically we can see that number 1 is going to be at least stable just because there's only one double bond as compared to 2, 3, and 4, which have two double bonds. Moving on, we're going to look at which one is conjugated and which one is not conjugated. So we can already rule out number 3 as being in this position just because that it's isolated position. There's more than one single bond in between the two double bonds. So we can already put that there. And then now we're just looking at 2 and 4. Well, we know that 2 is actually going to be more stable just because they're in a trans fashion, rather than here they're in number 4 they're looking at it's going to be this is in a cis fashion. So that's your ranking for least stable to most stable. Going down, we're looking at the MO theory, molecular orbital theory, and the atomic orbital theory. So for this question, we're looking at to draw an atomic orbital overlap for 1,3-butadiene. So the first step is just to draw the actual molecule. So let's see. So that is 1,3-butadiene. And then how I like drawing these is that at every single point where there's a carbon, take this, like right here, right here, right here, right here, where the double bond starts and stops. I just like drawing this. And this dumbbell shape actually represents the p orbitals because p orbitals are actually in dumbbell shapes, and it is where the electrons are actually interacting in these p orbitals where you can make these little bonds here. So this is how I like doing it. So that's how you draw the atomic orbitals for 1,3-butadiene. And to answer the latter portion of this problem, there's 4 p orbitals that overlap. You can see that by looking at here. So here's 1, 2, 3, and 4, and they overlap. So going down, we're looking at this molecular orbital chart for 1,3-butadiene. So this question is just asking you, what does the shading represent? Well, the shading represents, as you can see, there's some blue here, some red here, or if your paper is black and white, one is a little bit darker than the other one. But basically, the shading represents orbitals that are in the same phase. So we can just write that down. Okay, so you can see that this blue area right here, that's one phase, and then the red down here is one phase. And then over here, one phase, and so on and so forth. And as the phases change, as here is red and blue, as you can, let me see, right here, we can see that there's a node in between them just because that these phases are not the same. If this was also blue, let's see. If this was also blue right here, then there would be no node, and then just look like this one right here. Sorry, I'm drawing so many arrows. So looking at this question right here, how can we determine which orbital is LUMO? So we have to understand what LUMO stands for. So LUMO stands for lowest unoccupied molecular orbital. So looking at this one, it says in this case, it's the third molecular orbital. So it's going to be here 1, here's 2, and here's 3. So already here you can see that it's labeled at LUMO for you. And I like how LUMO stands for is the lowest unoccupied orbital. So you can see here that, right here, I'm going to zoom in a little bit. Over here you can see that here's occupied, this one's occupied, and this is the first one that is unoccupied, therefore making it the lowest unoccupied molecular orbital. So we can determine it by seeing which one. So therefore we can see that this is the first unoccupied orbital, so therefore it is the LUMO. So something that I would like to see that this an example, if this is actually how things look right here. Let's just say that this was our molecular orbital scheme right here, and this is now it's asking us for which one's the LUMO, which one's the HOMO. So the HOMO means highest occupied molecular orbital. So now this one's going to be the HOMO, and this one's going to be the LUMO, just because of what they stand for. So this is just an example that I just, gave just to just to show that the LUMO HOMOs, they just change depending on how many electrons there are. But for 1,3-butadiene, the molecular orbital that was given to you is the correct one. So we're going to move down and to number 4. So this one, it's a basic 1-2 addition or 1-4 addition. And in the notes or in the books, you'll see that 1-2 addition happens at lower temperatures. Lower temps, and then 1-4 addition is going to happen at higher temps. And how I like to remember is that 1-4 is bigger than 2. 4 is bigger than 2, so therefore 1-4 is going to be happening at higher temperatures. So something else that you can see a characteristic of 1-2 addition and 1-4 addition is that 1-4 addition, the alkene, the double bond is actually going to shift, as you can see in this little note right here. The double bond is going to shift, whereas in 1-2 addition, it actually just stays where it is. So you'll see a greater example of this in the next problem, which is draw all mechanisms to account for all possible products. So this one it's going to get a little filled here, so just kind of follow along. So of course, when we're doing this one, the first step is that you're going to draw this out. The first step is that the double bond from the diene is actually going to come over here and take the hydrogen from the chlorine. This bond's going to break and go over to the chlorine. So I'm going to go down. So this is where we're going to be getting 1, 2, nope, sorry, that's going to look ugly. Right here and over here because there's a lack of carbons. And then the Cl is going to be over here because it has a lot of carbons. Okay, so over here, there's 2 routes we can go. Here's the first route, and then here's the second route. So the first route is that there's going to be no methyl shift. So the first route is that there's going to be no methyl shift, and that the chlorine is just going to straight attack the carbon right here. Make sure you draw your arrows correctly. and then it's going to create a bond there. So this is one possibility. The second possibility is that there's actually going to be a shift. So I'm going to draw that out right here. And that there's actually going to be a shift that this double bond is going to move over here to account for this positive charge. And that your new product is going to look like this. And then now the chlorine is going to attack the new carbon, the new carbon that with a positive charge. And then your answer is going to end up like this. Now, if you just look at the first two right here, the first two possibilities, they're actually the same thing. It's just that you flip it, like you pancake flip it, and it's just literally the same thing. So these two, these two right here are actually the same product. So keep that in mind. So then that's going to be our first route, right? So we're looking at our second possibility. So our second possibility, what we're going to do is I'm going to look at the other double bond. So I'm going to draw this out. Okay, so in this scenario, this double bond over here is going to go over, grab the hydrogen. It's going to break. And then you're going to end up with something that looks like this. Like that. And then now we have two routes again. One, first route, and the second route. So then the first route is just going to be like the one we did before, where the chlorine is going just to attack the carbon right here without any shifts going on. So our answer over here is going to look like this. Like that. The second route is that there is actually going to be a shift that's going to happen. So I want to draw this again, right here. And the shift that's going to happen is that this double bond right here is going to come over here and accompany that. So then we're going to have something that looks like this. Oops. Like that. The chlorine right here is going to attack this carbon. And then your product is going to look like this. This one. So I'm going to box all of our answers in this, let's see. In this like bright pink right here. Actually, I'm going to highlight it right here. So this is going to be our 1. Or they're together 1. Going to be 2. And this is going to be our third one. So in reality, even though if there is going to be 4 products, but 2 of the products are exactly the same compound, so in reality you actually have 3 products. So the second part of this question is that which product is going to be favored at low temperatures and what's going to be favored at high temperatures. So you can just look at the mechanisms that we just drew, and the ones where there's actually a shift is going to be high temperature. So we can just come in and just kind of look at it right now. You can also label these 1, 2. So this one's actually going to happen at low temperatures. This one's going to happen, this 1, 4 is going to happen at high. This one right here is going to happen at low heat. It's 1, 2. And this one right here is 1, 4. It's going to happen at high heat. High heat, okay. So that goes for A. So now we're going to go over to B. And then for B, it's just going to be asking to draw the major product of the following reactions. So we're just going to go on and look at these, okay? So automatically, what we can turn our attention to are just these temperatures right here. And we're going to just look at these and just go, okay, well, negative 78 is it's definitely a low temperature. So this is going to be 1, 2. 40 degrees Celsius is actually pretty high, so it's going to be 1, 4, and 65 is even higher than 40, so it's going to be also 1, 4. So how are they looking at these? Numbering them. So we can just number these 1, 2, 3, 4. 1, 2, 3, and 4. And then let's see. 1, 2, 3, and 4. So let's see. So looking at this first one right here, BR2, we already know it's going to be adding at the 1, 2 position. So it's going to be 1, 2 position. So when we do 1, 2, or 1, 4 addition, what we're going to do is that we're going to actually dissolve the double bond right here. So it's going to turn to a single bond in compensation for the 2 BR bonds it's actually going to make. So I'm going to draw the product right here. So the 1, 2, 3, 4. So that's where our original carbons are. But because this is 1, 2 addition, the bromines just got added at the 1 and 2 position. So moving on, we're going to be looking at our second problem. This is going to be 1, 4 addition. So something that we have to remember is that when I actually give you the product, it's not going to just be as simple as just adding a chlorine at the 1 or 4 position. That 1, 4 characteristics also have an alkene, like the double bond is going to be moving around. And that's a characteristic of just 1, 4, because we're going to either have a methyl shift or a hydride shift, most often a methyl shift. So you can do the mechanism on the side for this and see where the shifts are actually going to be happening, because remember, here's a little review of that, carbocation prefer to be in a tertiary position. So this, the one I drew right here, is more stable than something that looks like this. So always, if there's a possibility for that carbocation to be in a more stable position, it will be. So it will rearrange for it to turn from, let's say, a secondary to a tertiary. So that's something you have to keep in mind when you're doing these things, that if there is a possibility to be more stable, it will be more stable. So enough talk. For the second one, this is what it actually looks like. There you go. And then for this one over here, looking at lower, the Cl2, since the Cl2, we're going to be adding 2 Cls, and it's 1, 4 position. 1, 4 entails that there's going to be a methyl shift, and then Cl2 means that there's going to be 2 chlorines added at 2 different positions. Here's going to be the 1 and the 4 position. So here's what the compound looks like. There you go. Kind of looks ugly. Sorry about that. So that goes for, that's all for this part B here. So we're going to be looking down, and this is where actually we're going to be looking at Diels-Alder reactions, or paracyclic reactions, and where we combine a diene and dienophile. So, so this is going to be the generic form, and over here, what this little diagram is showing you is that we have to remember that single bonds can rotate. Single bonds have free rotation, and double bonds cannot because they're locked. So because single bonds can rotate, we can actually take a trans diene, as we can see right here, and rotate it into a cis. And after we rotate into a cis dienes can, perform paracyclic reactions or Diels-Alder reactions, and that's basically all what this little diagram is telling you over here. So looking at the question that precedes this, that follows this, number 5, is circle compounds that can exist in cis conformation cross out components or compounds that cannot exist in the cis conformation. So something that we also have to keep in mind is that if the bonds are in a ring, you cannot rotate them. Only just regular alkenes can rotate. So this one can rotate, but this one is already in a diene or in a cis conformation, so this one automatically will work. Though this one cannot work. Sorry, this is what I meant. That this one cannot work because, as what I highlighted right here, is in a trans conformation, and then some people might just be thinking, oh, that's fine because we can just rotate this. Unfortunately, we can't do that because this single bond and this whole actual molecule right here is actually in a ring, and when it's in a ring, it can't rotate because then you're just going to strain the ring. You're just going to turn into different conformations where it doesn't want to be, because rings are planar and they're already far away from each other as possible. So when you try twisting it, you're actually making some compounds or some atoms go closer to each other where they don't want to do that. So we can't do that. They're already locked in. They can't turn. So this one can't do anything about that. This one, same thing. It might be hard to see, and this was actually on a test. But this right here is a trans, and no, it can't be a diene because it's not an cis conformation. It's in a trans conformation, and no, you can't rotate it because this single bond right here is in a ring. This one's also a no. This one right here, although it's in a ring, we don't need to rotate it because this is already in a cis conformation. So this is a-okay. Looking at this one is in a trans conformation. You can see it right here, little zigzag. And you're like, oh, but I can't rotate it. No, you can rotate it because it's not in a ring. There's no double bond in between them. So this is free to rotate, and you can feel free to manipulate that into a cis conformation to be able to get what you need. So this last one right here is actually a pretty cool one. You can see that this is a trans, and we need it to be a cis. But you're looking at it here, it's like, oh, there's a ring right here. Well, this ring we don't care about. We don't care about this ring because it's the single bond that we're interested in is not included in this ring. If it's in a ring, it can rotate. But if there's a ring that's kind of, off to the side, then we don't care about that. We don't care about that. This doesn't bother. This little ring right here doesn't bother this rotation of this sigma bond on the side. Okay, this one can rotate. So this one can definitely turn into a cis, and this definitely can participate in Diels-Alder reactions. So only among these, among these 6, only 2 don't work, and that's the second and third one. So going down is this little diagram right here is actually showing you a very basic Diels-Alder reaction. So basically what you have to just do is you have to fill in the little arrows. So always you're gonna have to take this little these electrons right here connected over here. This one's gonna move over here, and then this double bond right here is gonna move into right there, and it's gonna tuck it right into there. And then this is actually gonna make a hexagon. It's going to turn into that. So something that might be difficult when you're actually doing these is like, oh, how do I know what to draw? How do I know it's going to turn into a hexagon, a heptagon, or an octagon? The easiest thing, and it's really easy to miscount carbons, is to count the carbons. So over here we have 1, 2, 3, 4, 5, 6. And these 6 carbons are going to be coming together, joining together. So 6 carbons right here will translate to this, which is just a, regular smingular hexagon. And over here, where there's a electron donating group, electron withdrawing group, it's very important to be able to number these carbons and make sure that after you do the Diels-Alder reaction, that you can put these groups, these substituent groups, to which carbon they belong. And that's something really important, something that can definitely make a mistake on. So just be very careful about that. So this one is actually a fairly simple question. So why do Diels-Alder reactions favor low temperatures? Well, it's because at high temperatures, they'll just break apart. So if it's high temperature, so let's just take this little part and down here. That going this way is going to be at high temperatures. At high temperatures, your ring will break apart and then go back to the 2 pieces that made it in the first place. Going this way, it's going to be favored at low temperatures, at low temp. So when you want to do a Diels-Alder reaction, you have to make sure that's at low temperature. That way you can actually keep the product that you made rather than revert it back to the 2 reactants that you put in to try to make your product. So that's the reason why Diels-Alder reactions are more favorable at low temperatures. So we're going into the last part of this packet right here. This packet is actually kind of long. It's just that we're just going to be putting all the knowledge we have together and just making these Diels-Alder reactions and predicting the product. So the first one is actually very similar to the generic diagram that was given above. So what we're going to do is that we're just going to take this, drag it over here, and over here. So 3 arrows. So we're going to be connecting, let's see, we're going to be connecting 1, 2, 3, 4, 5, and 6. So we can just draw a hexagon because there's 6 in there. The electron's going to be over here on this side. So we can just draw right here. Remember the methyl group up here. And this is going to be carbon 1, which is right here. And then there you go. That's your answer. So now we're going to be looking at something a little bit more complicated where there's these 2 groups attached. And not only that, but this one's actually a triple bond. So something that we remember is that triple bonds actually have 2 pi bonds and then 1 sigma bond. So when you're moving electrons around, you're just taking out 1 pi bond. So you're just going to end up having 1 pi bond and 1 sigma bond. So what I like to think about is that 3 reduces to 2, and then 2 reduces to 1. So what I mean by that is that triple bonds get reduced to 2, double bond, and then double bonds get reduced to single bonds. And then you'll see that when we actually do this. So we don't have to worry about this conformation because this is already a cis conformation. And then we have to worry about where what gets attached to what, because this is actually a symmetrical dienophile. So what we're going to do is just going to do our regular little arrows. Let me erase this so that we don't really get confused. So it's going to be over here, 1, 2, and 3. So again, this is involving 6 carbons, so we can just draw a hexagon as our little skeleton. We already know that these 2 carbons are going to have a double bond because that's where the electrons ended up. But we're also going to have a double bond over here. That's because that this was a triple bond right here. If that was actually a double bond, then we can just leave this one as a sigma bond. But because it was a triple bond and we only moved 1 away, then it's going to have a double bond. So something else that's very important is that we have to see where our substituents are. So there's 1 substituent here, 2 here, right here. So we have to know where these are. So what you can do is that you can actually start labeling them. Give me 1, 2, 3, 4, 5, and 6. So when you label these, this is going to be carbon 1. So automatically we can just draw a little methyl group here and just so on and so forth, 2, 3, 4, 5, and 6. When you know 5 and 6, we're going to have the 2 CO2 CH3 bonds. And that's your answer for the second one. Moving on to this one, something that you'll see in your notes is that when you have a ring, when you have a ring and you're actually trying to do this reaction, what you have to do is remember that rings are planar, so just kind of pretend that they're paper. So when you do have to do these reactions, you actually have to move this part that I'm highlighting right here. You have to move it up, like fold it up like a piece of paper. And that way you can get to these 2 carbons right here, so you can do the reaction. So I'm going to do it, and then you'll see what I mean in a little bit. I'm going to move this over here, 1, 2, and 3. And this one is actually going to be same thing, 1, 2, 3, 4, 5, 6. It's going to be 6-membered ring. Okay. But now you're looking at, we'll just move everything and put everything in place. So this is where it's going to be our double bond, like everything else that we've done before. This carbon right here has 2 CN groups onto it. So we can just put this right here, CN and the CN. Now, our big question is, what are we going to do with this part that we just folded up? So there's 1 carbon right here, 1 carbon that I have to worry about. So where do we put that carbon? So that carbon, like I said before, gets folded up. So what you can do to represent that, you can actually just draw the 1 carbon here and then just connect it right here. So this is what we call a bicyclic compound. And it's because there's 2 rings. Ring number 1 and then ring number 2. That's why it's called bicyclic, 2 rings, or, like that. So what you can also draw this into, you can also draw it looking like this. It's like a little table that kind of got bent. Here's your double bond, your 2 CNs. Make sure you draw them in either endo or exo. And then here's your little carbon right here, and then you connect it right here. So these 2 are actually the same thing. You can draw either this way or you can draw it either this way. It doesn't really matter. But just be able to know how to interpret this and how to translate this into that and vice versa. So looking at the very, very last one, kind of could look confusing, but this is a cis. It's 100% a cis, and all you have to do is just have to turn it around. So this is what I mean. You can turn it to look like this. Same thing. Here's a little cis right here, and it'll be easier for you. It's easier for me to look at it and then to do our little reaction. So I'm going to do signature just 1, 2, 3, and then you can just draw our products. And I'm going to draw our product, and I'm going to draw it out right now. So every single time I do this, I want to draw the skeleton of it out. Like that. And that's the 2 carbons right here. So the 2 carbons I'm talking about is this one carbon right here is actually this carbon and this carbon. So like every other parasitic reaction we've did, the electrons end up here. And this 2 carbons is pointing up right here. There's 2 CO2CH groups. 2 groups right there. And then, let's see. And that's it. So, something to take away from this last problem is that you can manipulate your diene or dienophile to fit the Diels-Alder reaction. So over here, if this was a cis, if this was trans, let's see. If something is trans, like this, and it's in a single bond, you can turn it to make it into a cis, so you can be able to do reactions like this. If you need to turn things, you need to fold things up like in this problem, you can do that. So that way you can just get your Diels-Alder reaction. So that's the end of this section over here. Fairly straightforward. Very straightforward in the things you need to know for this chapter. But these are just basic Diels-Alder reactions you'll be seeing. And then everything else you'll learn will just be in the next few chapters, which will probably be covered by someone else. So I hope you guys found this helpful. I hope you guys learned a few things from here. Hope you guys enjoyed.